Okay, so in this video, we are going to be talking about some common Fourier transform pairs, as we call them. Okay, so we're going to be finding some Fourier transforms of functions, and these are going to be what we call Fourier transform pairs. So one function in the time domain, and then its Fourier transform in the frequency domain. And the ones we do in this video are going to be relatively simple, but they're going to show up a lot in this class. That's why I'm calling them common Fourier transform pairs. So let me just remind you what the Fourier transform formulas are. So we have this inverse Fourier transform, which is our way of writing f of t as a big integral of these complex exponentials multiplied by the Fourier transform at that frequency, omega. Then we have to add up or integrate over all of those omegas. And then also we have a formula for getting the Fourier transform itself, which is just going to be integrating f of t times e to the negative j omega t dt. Okay, so there's going to be a future video about Fourier transform properties, but there is one simple one that we're going to need in this video, and that is that the Fourier transform is linear. Okay, it's a linear operator. Linear. Okay, so let's see why that's true. Okay, so what happens when I take the Fourier transform? This is my symbol for taking the Fourier transform. What happens when I take the Fourier transform of some constant times a function? Well, I'm just going to use the Fourier transform formula right here and plug that whole thing in for my function. So I get a times f of t e to the negative j omega t dt. Now, of course, I can take the a outside. And I'm just left with a times the Fourier transform of f. Okay, so when I take the Fourier transform of a constant times a function, I just get that constant times its Fourier transform. Okay, so that's kind of a scaling property. And the other property we need to say that this thing is linear is what happens when I add two functions, f of t plus g of t. Again, I can do a similar thing, just get f of t plus g of t, e to the negative j omega t dt for the Fourier transform. Now I can split up this integral into two. I get f of t e to the negative j omega t dt plus the same integral g of t e to the negative j omega t dt. And of course, this is just the Fourier transform of f plus the Fourier transform of g. Okay, so the Fourier transform of a sum is just the sum of the Fourier transforms. That's the additivity property. And these two together, just like we saw for linearity in systems, linearity in these functions, like f of t, is a similar thing. You have scaling and you have addition. Okay, so that means in general, the Fourier transform of like a f of t plus b g of t is just going to be a times the Fourier transform of f plus b times the Fourier transform of g for any constants a and b and any functions f and g. Okay, so this is linearity, and we're going to be using that in this video. Okay, so let's start off with a couple simple ones. So what is the Fourier transform of the delta function? How about that? What is the Fourier transform of the delta function? It turns out it's just the constant one function. Okay, so the delta function in frequency actually contains all of the frequencies, okay, with the same magnitude. Okay, so this is just the constant one function in frequency. That's the Fourier transform of delta. So what it's saying is that you have to, here, the Fourier transform of delta, if it's just one, you have to add up all these complex exponentials with any frequency, okay, to get the delta function. Okay, so that's what this function looks like in frequency. I'll just leave that there. Okay, so let's show this. So let's take the Fourier transform of the delta function. Okay, Fourier transform of the delta function. So I do the integral of delta times e to the negative j omega t dt. Well, from the delta function properties video, we know that this integral of a function times the delta function is just going to pick out the value of that function being multiplied by the delta function, where the delta function is located. Well, the delta function is located right at t equals 0, right? This is the delta function. It's right at t equals 0. So I just want to pick out the value of this function when t equals 0. So e to the negative j omega times 0. But of course, that's just 1. Okay. That's pretty easy. What about a shifted delta function? What's the Fourier transform there? Turns out it's going to be e to the negative j omega t naught. Okay, and let's see why that's true. It's very similar. Just going to integrate the shifted delta function times e to the negative j omega t dt. Again, I have an integral of a shifted delta times a function. It's going to pick out the value of this function where this delta function is located. The delta function is just located, it's just shifted to the right by t naught. It's located right at t naught. Yeah, that's what the value of t that makes this argument 0, t equals t naught. So I just want to pick out the value of this function at that location, t equals t naught. So I get e to the negative j omega t naught. There you go. Okay. Now let's see what happens when I have a delta function in frequency. Okay. What is the inverse Fourier transform of that delta function in frequency? Turns out it's just 1 over 2 pi. It's going to be very similar. Let's just look at the inverse Fourier transform now. So the inverse Fourier transform formula is 1 over 2 pi times the Fourier transform times e to the j omega t. So I'm going to look at the inverse Fourier transform of delta of omega. And again, it's the same thing we've already done twice now. We're multiplying a delta function times another function, and it's going to pick out the value of that function where the delta function is located. In this case, at omega equals 0. So I'm going to get 1 over 2 pi times e to the j 0 times t. Of course, that's just 1, so we just get 1 over 2 pi. Okay. Now to do a similar thing as we did above, what happens when I shift in frequency? How does the inverse Fourier transform change then? When I shift the delta function in frequency, I'm going to get 1 over 2 pi times e to the j omega naught t. And some of these properties we're going to see in more generality in a future video, but it's okay. We'll just do it for practice here so we get some experience. Okay. Like for instance, we're going to see what happens in general when you shift in time or shift in frequency. This is good. We're getting some more practice now. Okay, so let's do the inverse Fourier transform formula again. Going to have delta of omega minus omega naught, e to the j omega t d omega. And we're going to pick out the value of this function, where this delta function is located. Well, it's shifted to the right by omega naught, so it's located right at omega naught. So I'm going to pick out, I have my 1 over 2 pi, and I'm going to pick out the value of this function where omega equals omega naught. And there you go. That's what we want. Okay, so integrating with delta functions is actually relatively easy. All right. Now let's see what happens when we want to take the Fourier transform of a cosine function. Okay. And if you think about it, what frequencies are present in this cosine function? Okay, what frequencies, like what complex exponentials, are present in this cosine function that I would want to integrate up these complex exponentials multiplied by something, okay, to get my cosine function? Well, it's sort of like exactly what we saw with Fourier series, and we'll see the connection between Fourier series and Fourier transform later on. Okay, but what complex exponentials are present in my cosine function? Well, if my cosine function has frequency omega naught, I'm going to have e to the j omega naught t, and also e to the negative j omega naught t. We're going to have the frequencies of omega naught and negative omega naught. And it turns out those are exactly the two delta functions, the two frequencies we have in our Fourier transform. Turns out we'll get this pi constant, and you'll see why when we actually do the math. But then the two frequencies are going to be a delta function located at omega naught, that's one of our frequencies in this cosine function, plus a delta function located at negative omega naught, which is the other one of those complex exponential frequencies. Okay, so let's see why this is true. Let's take the Fourier transform of cosine of omega naught t. Okay, and what do we want to do? Well, we already know what the Fourier transform of these complex exponential signals are. So if we can manipulate our cosine, just like we saw with Fourier series, to be a sum of these complex exponentials, then it'll be very easy to take our Fourier transform. Okay, we already have that Fourier transform pair. So how can we do that? Well, of course, we can write cosine as 1/2 e to the j omega naught t plus 1/2 e to the negative j omega naught t. That's from that Euler type formula we've seen a million times. Now we're going to use that the Fourier transform is linear. Okay, what does that mean? That means if I have, this is exactly what I said before, a constant times one function plus a constant times another function. Okay, the Fourier transform of all of that is just going to be that constant times the Fourier transform of the first function plus that constant times the Fourier transform of the second function. Okay, that's the linearity of the Fourier transform. And now what's the Fourier transform of this function? Well, since the Fourier transform is linear, whenever I have one of these Fourier transform pairs, I can always multiply both sides by a constant and get another Fourier transform pair. All right, that's what that scaling property of the Fourier transform is saying. Okay, so if I just multiply both sides, actually I could have kept this 1/2 even, but if I multiply both sides by 2 pi, I get that e to the j omega naught t is a Fourier transform pair with 2 pi delta of omega minus omega naught. Okay, so I'll leave that there for a second and then I'll erase it once we use it. So this is just going to have this as its Fourier transform. Again, just bringing this 2 pi to the other side since Fourier transform is linear. So it has that scaling property. You can see this 2 will cancel that 2, and all I'll be left with is pi times that delta function. Now what happens when I do the same thing over here? Well, now I just have to plug in negative omega naught, right? Because I have a negative omega naught. Now I'm going to get delta of omega minus negative omega naught. In other words, omega plus omega naught. But again, those twos, that 2 and that 1/2 will cancel, and so I'll just get pi times delta of omega plus omega naught. Okay, so that's just using this property above and the scaling property. Okay, all right. And what does this look like? I'll just draw it so we have an idea. Okay, what does this look like in frequency? Well, I'm just going to have two delta functions located at negative omega naught and positive omega naught. And they're both going to have height or area pi. Okay, so it's really that the area is pi, but remember we denote the height of these functions by their area, pi in this case. Okay, so that's what the Fourier transform cosine would look like. And again, it makes sense that it just has these two frequencies because those are the two frequencies, the complex exponential function frequencies that we see in our cosine function. All right, let's do the same thing, but for sine now. And it's going to be similar. It's just now we're going to have pi over j times delta of omega minus omega naught minus delta of omega plus omega naught. And we're going to follow a similar technique here. Fourier transform of the sine function is just going to be the Fourier transform. Let's express it in terms of those complex exponentials. So we get 1 over 2j e to the j omega naught t minus 1 over 2j e to the negative j omega naught t. So that same Euler type expression we derived before and have used a million times. Now I'll use the linearity of the Fourier transform again to say this is just 1 over 2j times the Fourier transform of e to the j omega naught t minus 1 over 2j times the Fourier transform of e to the negative j omega naught t. And we already saw above what those Fourier transforms were, right? Fourier transform of this guy was just 2 pi times this delta function. Okay, so when I have that 2, it'll cancel this half, and I'm left with just pi over that j times delta of omega minus omega naught, the delta function located at that frequency. Okay, and then I'm going to have a minus a similar thing, right? Fourier transform of this is 2 pi times delta of omega plus omega naught. The 2 will cancel there. I'll be left with a pi divided by that j. And I'm just going to have a delta of omega plus omega naught here. Okay, same as above. Pretty similar, I mean. Same process. Okay, so that's the Fourier transform of the sine function. Now one last one. Let's look at the Fourier transform of e to the negative at times a unit step function. And this is going to be where a is positive. So what does this function look like? It's just a decaying exponential. Right? It's just a decaying exponential, but it starts when t is 0. Okay, so it's 0 and then a decaying exponential after that. That's what that function looks like. Okay. And it turns out its Fourier transform is 1 over a plus j omega. And we're going to show that right now. Okay. I'm going to show that right now. So let's look at the integral of this function. We're taking its Fourier transform, e to the negative j omega t dt. Okay. Well, this unit step function is 0 whenever t is negative. So it's going to zero out this entire integrand whenever this variable is negative, that t variable is negative. So I might as well just start integrating right at 0, because everything before that, I'm just going to be integrating 0, which is 0. So I get e to the what? Well, now I can combine these exponents, and I just get negative a plus j omega times t. Okay, and now I can do this integral. So I'm going to get 1 over negative a plus j omega, e to the negative a plus j omega t, from 0 to infinity. So now what happens when I plug in infinity? Well, I think we saw this before. E to the negative at, e to the negative j omega t. When I let t go to infinity, this is a decaying exponential. As t goes to infinity, this part is going to go to 0. Okay, and what's going to happen to this part? Well, that part's just going to keep oscillating around and around the unit circle. That's not going to go to anything. But because this first quantity is going to 0, it's going to force this entire product to actually go to 0 as well. Okay, so the magnitude of this function is going to be something going to 0 times something that's always 1. When I multiply something going to 0 times something that's always 1, I'm going to get something going to 0. And so the magnitude of this function is going to eventually hit 0, and the only number that has magnitude 0 is 0. Okay, so that means that shows that this whole function is going to go to 0. So I'll kind of keep this a little small to the side here. And what does that tell us? Yeah, that's what I'm using right there. That tells us that when I plug in infinity, I'm going to get 0, and then minus what I get when I plug in 0, which is just 1. E to the 0 is 1. So that's going to cancel that minus because I'm subtracting what I get when I plug in 0. And I just end up with 1 over a plus j omega, which is what we wanted. Okay. There we go. Yeah, I'll leave it like that. Okay. So that's that Fourier transform, and we're going to see all the Fourier transforms in this video come up pretty often in the class, so definitely a good idea to go back through and make sure you understand all the steps we made. But yeah, that's about it for this video, and I'll see you in the next one.